Good evening, everyone. It's wonderful to see so many faces out there in the audience, and for those of you online, welcome. This is the latest installment of Argonne's Out Loud Public Lecture Series. My name is Megan Clifford. I'm the Associate Laboratory Director for Science and Technology Partnerships and Outreach here at the lab. Tonight, we will spotlight the growth of quantum science and technology and the role Argonne and partners are playing nationally and regionally in shaping its future. Before we dive into tonight's program, I want to share a few housekeeping notes for those of you here in the room and for those of you who are tuned in online. For our virtual audience, when you joined, your camera and mic were automatically turned off. If you experience volume issues, please make sure to unmute the audio and use the volume bar on the Vimeo screen. If you'd like to use closed captioning, there is a button you can select on the lower right-hand side of your screen. Captioning is not always perfect, especially with some of the scientific terms, so please bear with it. If you're having any trouble, please send an email to outloud@anl.gov and we will help troubleshoot. For our in-person audience, we are recording the event, so by participating, you are consenting to be recorded. The recording will be available on Argonne's YouTube channel within a week. In case of an emergency that would require us to exit this building, behind me you can see a diagram of the multiple emergency exits from this room. In case of an emergency for a weather event that would require us to leave this room and proceed to weather shelters, behind me you can also see a diagram of the path we would take. Argonne staff are prepared to direct you to these shelters if needed. If you become aware of an emergency situation, alert members of Argonne staff who are here or call 630-252-1911 from your cell phone. Lastly, whether you're online or in person, we operate under Argonne's Code of Conduct. Argonne's core values of impact, safety, integrity, respect, and teamwork govern how we act as an Argonne community of employees, collaborators, users, students, vendors, and visitors. We are committed to creating a safe and welcoming environment. It is expected that we will treat each other with respect, professionalism, and civility. So thank you for participating. Having covered those important items, I'd like to share some thoughts on tonight's lecture topic. We're gathered here to celebrate more than just a scientific frontier. We're here to explore a vision for the future. Quantum is a platform for discovery that is redefining how we solve problems in areas such as computing, communications, material science, and national security. And here at Argonne, we're proud to be part of the national strategy to accelerate quantum innovation, advance the frontiers of science, and translate research into impact. At the same time, the progress we're seeing across Illinois reflects something bigger. A recent Crain's Chicago Business article highlighted how Illinois is establishing itself as the nation's center for quantum technology development. That narrative illustrates how public and private institutions are forward-thinking, creating infrastructure that positions Chicago and the Midwest as a hub for sustained scientific and economic advancement. You'll hear more about that tonight. The term quantum prairie, the title of tonight's event, can be seen as a metaphor for possibility, a wide open landscape where pioneering research, technical talent, and forward-looking investment can take root and flourish. Argonne is contributing to this effort through the Argonne Quantum Institute, our leadership in QNext Quantum Center, our work with industry and academic partners, and our role in building the backbone of quantum networks and next-generation platforms. Our work in the region is contributing to a vital national effort to keep the U.S. at the forefront of quantum research and development. We're also committed to helping the broader public understand what quantum means and why it matters. Quantum can be complex, but its implications are far-reaching. Events like tonight's help bridge that gap, creating space for conversation, imagination, and understanding. Whether you're a business leader, a policymaker, a student, or a science-curious member of the public, your presence speaks to the growing interest in and relevance of quantum science. So thank you for joining us. We're excited to share this journey with you. And now it's my pleasure to introduce someone who's been at the forefront of Argonne's quantum efforts. Please welcome Michael Norman, Director of the Argonne Quantum Institute.
All right. Thank you much, Megan. So, this is the International Year of Quantum. What happened? Oh, there it is. Oh, good. So, we're celebrating a 100-year anniversary of the first serious theory of quantum mechanics. So, people want to say that's a century ago. That's sort of old now. Why are people interested in this now? And this is because a lot of the stranger things that have been predicted by quantum mechanics, we did not have the technology to realize them. We now have the technology to realize them. And so this is why you see all the attention that's been given to quantum the last few years. So since we're here, public, I thought tell you a little bit about what quantum is all about. So usually people talk about Schrödinger cat being like half dead, half alive. I prefer the Cheshire Cat. So people probably know about the Cheshire Cat, right? You always saw the Disney cartoon, you know, Alice in Wonderland. And the Cheshire Cat sort of fades in and out of existence. It's here, then it's there. And this has a good representation of the wave-particle duality, that sometimes an object in quantum mechanics behaves like a wave, sometimes it behaves like a particle. People have taken this further. They've done little experiments where you have like two boxes, and you remember the Cheshire Cat in Alice in Wonderland, it sort of vanishes, but it leaves this grin. And they've been able to take like two boxes and put the cat in one box and this grin in another box. So this is a kind of strange things that happen when you get to the scale of the very small. So there's two concepts we want to talk about today. One is called superposition and one is called entanglement. So the second diagram shows a bit, a transistor. All your phones, all your electronics is based on transistors which either have an on state or an off state. So on state, off state, two values, it defines binary arithmetic. So this marvel that you see of modern technology, an iPhone, is nothing more than a fancy binary arithmetic machine, okay? So imagine you take the surface of the Earth and you say the North Pole is the on state of the transistor and the South Pole is the off state of the transistor. A quantum bit instead lives on the entire surface of the sphere. So it's not only just at the North Pole and South Pole like a classical bit in a computer, it exists over the entire sphere. Now, there's no free lunch. If you measure it, you either have to get on or off. So if it's on the North Pole, it's on. If it's on the equator, it has a half chance of being on and a half a chance of being off. This is a Schrödinger cat thing about being half dead and half alive. It's a little better than that because we were looking at a measurement axis along the north-south pole, but you could put it through the equator as well, and then it would say, okay, it's 100% chances on the equator. So it's pretty good. It's quite a bit more elaborate than a classical bit. But the real power comes when you entangle these things. So a quantum computer would have all these bits and they will be entangled. What do we mean by entangled? This is Einstein's spooky action at a distance. So if you have, say, some quantum object pointing in this direction, its pair maybe be pointing the opposite. And if you move this one, this other one automatically moves. It's almost like they're communicating at faster than the speed of light. Of course, they're not. How do you know? Because if this one's doing this guy has to communicate with that guy and say, what is yours doing? Yours is pointing this thing. And of course, communication is done classically. So it really doesn't violate the speed of light, but it's still pretty amazing. And so when you entangle these things all together, you can think of a quantum computer as like some giant hive mind. Think of it like the Borg in Star Trek. They all know what each other is doing. And so what it means is like a quantum computer, a functioning one, would be like some massively parallel machine. It would be the ultimate parallel computer where in some problems, all the answers you're interested in are actually sitting in the machine simultaneously. You're just pulling out the one that you're interested in. So it makes quantum computers qualitatively different than classical computers. Then you hear about quantum internet. Like, what is a quantum internet? So there's a theorem saying you cannot clone quantum information. So it's not like Dolly the sheep you can clone, but you can make a copy if you destroy the original. So if you think about that, that's sort of how the Star Trek teleporter works, right? The people on the platform, they disappear, they appear somewhere else. What's really happened is the original copy has been destroyed. And the same thing happens for quantum teleportation. You teleport the information by destroying the original. So why is it unhackable? Well, like I said, if you noticed before, when you measure it, it has to be on or off. So if you intercept it, it's like measuring the beam. And if you measure it, you'll know it either on an on state or an off state. And therefore, what you've done is you've altered the information. It's been forced to choose. And so the receiver knows that the information has been tampered with. So this is why we say a quantum internet is actually an unhackable internet. The last thing I'm going to end up with is a concept called ghost imaging. So imagine you're at the advanced photon source, very, very bright beam of light. It could fry your sample. What you do is you take a weak beam that illuminates the sample, then you take a strong beam that does not even image the sample, but is entangled with the weak beam. And the weak beam images the sample, and the strong beam, you measure it, even though it never touches the sample. And we call this ghost imaging. And of course, when they demonstrate this, of course, what are they going to use? Cats, of course, because cats are the mascot for quantum mechanics. So let me say a little bit about what we're doing here. As Megan mentioned, we have a quantum institute doing all sorts of things like materials, sensing, networks, simulations. We have a quantum center here funded by the Department of Energy. There are 5 of them in the nation. 2 of them are here. 1 is here. 1 is down the road at Fermilab. We have several quantum networks like I just described, some internal, some connecting us to Fermi, some connect us to University of Chicago. We're also part of the Chicago Quantum Exchange. We're part of the Quantum Startup Accelerator. We're part of something called the Block Quantum Tech Hub. And we have many interactions with quantum computing and other quantum technology companies. And finally, as you may have heard, the governor has decided to construct a new park on the south side of Chicago called the Illinois Quantum and Microelectronics Park that will be anchored by a PsiQuantum. And the director of this park is actually here tonight, and you'll be able to meet him as well. So thank you very much. We'll have the next speaker come.
Thank you, Mike. Our next presenter is Jiafei Zhang. Jiafei is a materials scientist here at Argonne, and she's going to talk about quantum materials. Let's please welcome Jiafei to the stage.
Thank you, Megan. Yes. So here I'm going to share with you a little bit on the quantum materials research we do here at Argonne within our material science division, as well as under this QNX center that Mike mentioned earlier. So before I dive into the materials related research, we ask the question of what is a qubit? This is a term that you probably hear every day when people talk about quantum that is at the core of quantum technology. As mentioned by Mike, if we take a step back to classical technology, 1 bit is basically 0 and 1 based on the voltage of the transistor, low and high, like your switch. That switch in your home, 0, 1, your code information. But for qubit, it's a quantum particle. It can be in different forms, but ultimately what it has is it leverages this superposition. You have 2 states as pictorially shown in there, 0 and 1. But it can be in any kind of mixture of the 2. You can imagine like that, just like you have a intensity tunable light switch at home. You tune the intensity depends on how you feel like, and then the information you can code in there is much richer than just on and off. But then what are the kind of physical forms? Well, it can be photon, a single particle of light that comes over, flies by, depends on the polarization, horizontal versus perpendicular, you have 0 and 1. And you can create superposition to represent that. And similar things apply for electron. You have spin up, spin down, as well as in atoms, you can have a two-level system. You can interface and control and manipulate to read information out, also in the context of tiny circuitry like superconducting circuit that you may have heard in the context of quantum computing. So now, given that is what is likely a qubit, and what are the actually things that one do in creating a qubit here at Argonne? We focus on semiconductor material, just like the ones you have in your computer and phones, and we're creating an artificial atom in it. You can start with a chip, and now what you want is you want to have a controlled atom. So here in the middle, I'm giving you a simple example of such an artificial atom, which is so-called a nitrogen vacancy center. What you do is, well, 2 atoms, please go away, and then I put a nitrogen atom in there and a vacancy nearby. And that gives you an artificial atom. And you can control the spin states to give you 0 and 1, and you can interface it with it to kind of write information in and retrieve information out. But everyone knows that quantum state is very delicate. If you leave it unperturbed, you put it on one direction on the pictorial sphere, you create it, then it's like, okay, the state stays there. But in reality, there are all kinds of perturbations that can cause the state to evolve and to change. Then your information gets compromised. And that type of interaction can come at atomic scale, like impurities in the materials and other like strain field and fluctuating field that the qubit sees. So basically, it boils down to like at atomic level, how one can control it. And here at Argonne, we create this artificial atom not only based on just nitrogen, we can do different items like germanium, tin, and even put rare earth ions into those crystals, depends on the type of application, with a fundamental goal of creating a robust qubit such that you could transfer information from point A to B, and that A to B could be just on the same chip for quantum computing. It could be between you and me, or between me and any random person on this continent that far away with fibers and things like that, that you could share information with using the laws of like entanglement. So that give you the kind of access to create such a qubit. Then you can tell there's all this interaction at atomic scale that one need to worry about, and this is what Argonne Quantum Foundry here can help address some of the questions of how we can tailor the interaction, how we can design qubit for different applications. Different applications have different figure of merit and different performance of qubit that one need, and correspondingly the type of noise and disturbance that you will worry about is different. So this Argonne Quantum Foundry is launched in 2023. It covers a 6,000 square feet space where we have all the tools starting from how you create the qubit in the material to start with, to like how you characterize it, how you test it. Some of tests you can do at room temperature. Some of tests you need to go to very low temperature, like even lower than your refrigerator temperature. So that is what are all the tools that I brought under one roof with a focus on semiconductor-based qubit platforms, with the hope to address this supply chain of creating the material, the qubit that is designed for a specific application. Here with a lot of interest in quantum computing, communication, and quantum sensing. And also this Quantum Foundry is open to students and researchers across labs with various internship programs that can work in the foundry to gain first-hand knowledge and experience with all the technique involved. And besides Argonne Quantum Foundry, we also leverage unique expertise within Material Science Division that focus on material synthesis to address the fundamental question of what are the interactions at play that can affect my qubit to make it less robust, and how we can, based on that understanding, to have a better design of qubit system for targeted applications. And then we can create them into a device with the aim to test it with real-world metropolitan scale U-Chicago quantum network that has multiple nodes within Argonne and connects Argonne to U-Chicago and even UIUC at Urbana-Champaign. And you could also see, because everything is literally atomic scale, which is like sub-nanometer, it's over like 100 thousandths thinner than your hair, you need something that get to that length scale to probe to help you better understand what happens at that length scale. So we have this advanced photon source that at Argonne that give you that access to probe and better understand what is going on and to help us to feed back into the design of the system. So with the last slide, I'm just give you a quick highlight of the kind of like different platform, different qubit that we work on. The one on the right is a single electron that we manipulate on neon surface and with superconducting qubits. And the two in the middle is basically on like semiconducting material, silicon carbide and diamond type of structures, as well as like rare earth based quantum memory platform that I'm leading here at Argonne as well. So hopefully I have given you a broad overview of the kind of materials-related work we do here at Argonne. So I'll transit to the next speaker then.
Thank you, Jaffe. Our next presenter is Salman Habib. Salman is director of the Computational Sciences Division here at Argonne, and he is an Argonne Distinguished Fellow. Salman is going to share a bit about quantum computing, simulation, and other related Argonne capabilities. So let's please welcome to the stage Salman.
Thanks, Megan. So everything should be crystal clear now, right? Quantum mechanics. So no, apparently not. So I mean, but this is nothing to be worried about, because Richard Feynman famously said that no one understands quantum mechanics. So this was, a very helpful thing for me when I was a graduate student. So, just keep that in mind. So I'm here to give you some context about quantum computing, what's happening at Argonne and other places. And we'll start with a very, very simple thing about the laws of nature. So the laws of nature are very strange, and this is something very, very, very easy to understand. The point is that the way we view the world is through a very limited window of our senses, right? So for example, if you think about acoustics, the range of the ear is about 10 octaves, and a piano cover is about 7. So you might say, well, musical instruments we can kind of understand because they're all within our auditory range. On the other hand, when it comes to electromagnetic waves, we can measure about 150 octaves, but the eye is only sensitive to less than 2. So we're basically not able to see the universe in its true glory. So when we do see it, sometimes you're shocked by like, how is this behavior possible? For instance, superconductivity was discovered without any idea of how it actually happened. And the same is true of even more mundane things like semiconductors. So it's very important to keep in mind that it should be no surprise that a lot of things that we deal with, we don't actually understand, but we can nevertheless manipulate through the fact that the math that we use actually describes the universe. And so by using abstract thinking, we can make progress. So important thing about this is that nature and technology, the understanding the rules of how things work, is also connected with how we develop technology. Now, some technologies can exist and can be extremely useful without actually understanding the foundations at all. Like, for example, construction. If you want to build a mud house, you don't have to know quantum mechanics at all. Just experience is sufficient. That there are wrong ways to build it and there are right ways to build it, and that's fine. But cutting-edge technologies rely on knowing the foundations. And a very, very good example of a technology that uses both quantum mechanics and general relativity, which are our deepest known theories, is the GPS. So all of you have it. You use it every day. And what's interesting about it is that there's an atomic clock in the satellites that keep them all knowing exactly where they are and how they are timing themselves. And at the same time, because they are about 20,000 kilometers away from us, the gravitational field of the Earth is sufficiently weak that actually the clock's frequency shift by an amount that due to general relativity, that if you didn't correct, would change your knowledge of where you are on the ground by about 10 kilometers per day. So this is actually very interesting. So the clocks are detuned before they're sent up to the satellite. So they speed up just the right amount when they actually reach the right radius. Another example, which is a kind of obvious one of quantum mechanics, is all of our electronics, things like lasers, which initially when lasers were developed, people said, well, that's a kind of useless thing. You know, what are you going to do with that? And of course, we all know that there's lots of things you can do with that. And things like MRI scans are all basically only possible because of our deep knowledge of quantum mechanics. So this is a point I just want to make, is that quantum technologies are technologies that arrive because we actually understand what we're doing, which is not always the case. So this is, I think, an important transition slide, which is that national labs, and Argonne being one, of course, are very interesting places because this is exactly where basic sciences and technologies come together in an effort to change the world. So, which I think is one of the major reasons for why national labs should exist. So let's talk a little bit about quantum mechanics and computing. Now, one thing that is pretty apparent, which should have been apparent from the first two talks, is that quantum mechanics is kind of bizarre. It allows for matter to be in what we would consider by standards of usual human experience to be in very peculiar states, or not even to be in peculiar states, but to be peculiar period, right? So you might say, okay, well, that's fine, but why do I care about it when it comes to computing? The reason you care about it when it comes to computing, that information, which is fundamentally what you do in computing, is you manipulate information. You take some input information, you do some stuff to it, you get an answer, right? You ask a question, the question always always has some information aspect to it. Now, the important point is that information is physical. It doesn't live in some abstract realm. Information has to be represented. So if I write a book, and let's say it's the only copy of the book, then all the information that I put in is in its pages. If you burn the book, the information's gone. And right? So it's very important to understand that if there's a fundamental notion of information is represented somewhere, and we have the fundamental theory saying it can only be represented in certain ways, then we might expect that how we deal with that information is different. So if the fundamental theory is quantum mechanics, then we may expect that quantum mechanics might tell us that quantum information is going to be different than our normal information. Now, usually, the strangeness of quantum mechanics is hidden. As we go around our daily activities, weird things don't happen to us, at least only occasionally. So a lot of this thing that quantum mechanics is weird was basically hidden, and people didn't really think about how it might affect quantum information theory. So relatively few people started thinking about this, and in the 1960s and the 1970s, and Paul Benioff, who used to be at Argonne, wrote a very important and influential paper, which people realized the influence later on, but where he basically said, given a purely quantum system with all its strangeness, can we actually compute with it? And he came to the answer that yes, you can. And he proved some theorem saying that yes, you can actually do it. Now that's fine, that's interesting, but so what? If the power of such a thing is no different than what you can do with a classical computer, then it would be a curiosity, but no more. But Peter Shor in '94 showed a very, very important result, which is that, yes, you can do something interesting with quantum computers that you cannot do classically, which is the famous problem of factoring. Now, I don't have time to explain this, but that's when everyone got excited. So it's about 30 years ago, right? Now, one of the big misconceptions that are around is that, oh, quantum mechanics should make every computational problem easy, and that is totally not the case. Now, why is that? The reason is that the detailed information that the previous speakers referred to is hidden inside a computer, a quantum computer, as not easily accessible. So you have to write a very, very clever algorithm such that the interference in a quantum computer is constructive when you want the right answer and destructive when it's the wrong answer, so that when you make a measurement, you hopefully only get the right answer. The other problem is that quantum states and the elements that go inside a quantum computer are extremely easy to disrupt and are extremely fragile. So they may last for a millisecond or something like that. But often we want to do calculations that will last for weeks or hours or minutes, whatever it is. So that's very difficult. The other big problem is that storing quantum information stably is extremely difficult, especially since you cannot make copies of quantum information due to something called a no-cloning theorem. So the best general application for quantum mechanics is simulating nature itself, which is a remark that's due to Richard Feynman. So to finish, in order to make quantum computers work, a major initiative is required, and so supercomputer-style initiatives, as the IQMP was discussed. And once a machine like this starts working, Argonne would be a prime host for large-scale machines, since we have such systems here. And we are working very closely with industry and governments to basically craft the future of quantum computing. So with that, thank you.
Thank you, Salman. Next up is Preeti Chalsani. Preeti is Senior Vice President and Chief Quantum Officer for Intersect Illinois, which is the only statewide economic development organization focused on bringing in new businesses, jobs, and investment into Illinois. Preeti is going to talk about the very active and robust Chicago area quantum ecosystem. So let's please welcome Preeti.
Good evening, everyone. So by now, hopefully, you've gotten a sense of how exciting quantum technologies, this new field, this new emerging area is, and what a big role Argonne is playing in moving this field forward. I hope to spend the next few minutes giving you an idea for why Illinois and the Midwest region is really poised as a hub, as a global hub for advancing the science and technology of quantum information, and what makes us successful. So let's see. First task, learn how to move the slide ahead. So this is sort of to give you a snapshot for what makes us this hub for this global hub for quantum technology. Hopefully, you've gotten a sense that quantum technology, quantum science didn't just come out of nowhere. It's a complicated science that brings into it expertise in the mathematical sciences, computer science, electrical engineering, chemistry. There's a lot of work, a lot of hard and innovative work that's being done in various fields that lead us to this moment where we're able to explore applications of quantum technologies and think about what implications, what advantages this can bring to the world. And we're fortunate to live in a place where we have powerhouse institutions like Argonne, like Fermi, like our universities, University of Illinois, University of Chicago, Northwestern, that have been doing decades of work to lead in these fields, in these adjacent fields, and have actually been at the forefront even of quantum science. Chicago had a quantum science and engineering program since 2014. And that was before quantum became a buzzword. It was the first place to have a PhD in quantum engineering. So it's not accidental that we are, at this place where Illinois is a hub for quantum technologies. It's because all of these institutions have been working towards it. This area is also a real engine for talent in all of the associated STEM and STEM fields. We have a whole variety of really top-notch programs in science and engineering at all of our universities and national labs that train the talent that you really need. If you don't have the talent, you can't do much in industry. And this region produces more talent than anywhere else in the country. That's what I would like to argue. You can see stats like University of Illinois produces more engineers. One thing that I recently started to think about in this way, if you look at the top 10 engineering schools in the country, and you count up how many top 10 engineering grads there are, Illinois has more than Massachusetts or California. That's really powerful. And I think people are realizing that. Companies are realizing that. And we're becoming a real magnet for companies and startups and researchers trying to do hard things. We also have a really progressive and inclusive educational policy. We're trying to really develop innovative programs to bring in our community college systems to be able to bring them into the workforce. Again, very essential to advanced technologies and the industry. And then, like, really important, we have this work. You know, everything starts for an emerging technology. It starts with the talent and with the science where it all starts. But you also need to have infrastructure where you can do this work. And we've already heard about all the amazing infrastructure at Argonne. All of our local universities, Fermi as well, have developed this type of infrastructure that is available to the public, that is available to startups and industry, that creates this environment where we can advance technologies. And even more important, and really what's being unique for our ecosystem, is that we've had catalysts like the Chicago Quantum Exchange, which brings together researchers, industry, policymakers, governments, federal and state government together to try to do more to advance this field. Duality was the first quantum startup accelerator. We have many other accelerators and incubators like Chain Reactions Innovations that helps us advance this field. That has been really critical in order to help us grow startups in the region. So over time, we've gone from 0 to now we have close to 14 startups working in this area. And again, that's more than most other regions have. We are also fortunate to live in an area where we have a really diverse industry base. Again, this is critical for an emerging technology where we don't know where the applications are. How can you explore applications? By having access to a whole region of industries like life sciences, finance, transportation, so you can see where can I explore applications for quantum. And what has also been really critical in helping us move along is a very extensive support from industry. We have over 50 different types of companies involved directly in quantum activities. Many of them have been hiring from our region, and many have been investing in the work that's being done here. And then, you know, something that really shows that what I'm saying is not just because I want to hype up what we're doing here, but as a validation externally. When the National Quantum Initiative was launched in 2018, the federal government funded 10 quantum research centers. 5 were funded by the DOE, 5 by the NSF, and 4 of those 10 are based in Illinois. This is clearly more than any other region. So that tells you that what we're doing is real and it's validated externally. And more recently, our state very uniquely has really stepped up in realizing what amazing work is being done here and supported quantum efforts with more than $700 million. This is really unprecedented. When I go to conferences, I hear about how this state or Texas or someone else is going to do things like Illinois, which really tells you we're at the forefront. And most exciting, you know, one of our most exciting initiatives over the last year has been the Illinois Quantum and Microelectronics Park. And I'll stop here because our next speaker is going to tell us more about it.
Thank you, Preeti. Next is a bit of a special guest. He was traveling back from an international trip, literally just arrived, I don't know, 2 hours ago. We weren't sure if he was going to make it on time, so that's why he was not advertised in tonight's program as one of the presenters. But we are so thrilled he made it. Harley Johnson, he is the Executive Director and CEO of the Illinois Quantum and Microelectronics Park. He is also a founder professor at the University of Illinois, Urbana-Champaign. Harley's going to talk about the Illinois Quantum and Microelectronics Park, as well as his perspective on the work that is being done in the region. So let's please welcome Harley Johnson.
Okay, so it's great to be here. I wasn't sure I was going to be here until about an hour ago. I don't have a set of slides to talk from, but I'll just tell you a few things about the project that we're working on, something we're just very excited about. And I should say, it's really nice to have an audience of community members who are interested in learning about this exciting work. So I'm a professor at the University of Illinois Urbana-Champaign. I'm an engineer and a scientist. I work on electronic materials and quantum materials. I've been here in Illinois for about 25 years. For the past, now a little less than a year, I've been in this role also as director and CEO of the Illinois Quantum and Microelectronics Park. This project has been something that's been in the works for a couple of years. A group of us got together about 2 years ago and started to think about how can the state of Illinois and the region, but focused on the state of Illinois mostly, position ourselves better to do something really impactful in science and technology broadly. This was motivated by some of the large federal investments that were going to be coming out a couple of years ago in the CHIPS and Science Act. We looked at our strengths and weaknesses. We looked at some of the things that you just saw that Preeti shared and that some of our colleagues from here at Argonne were speaking about. And we concluded that while some states and some regions are focused on semiconductor fabs and microelectronics manufacturing, very important, reshoring of that technology, we could see that the state of Illinois had a special opportunity to do something big in quantum, which in some ways is sort of maybe could be the successor to a lot of the work in microelectronics. So we're thinking about the next wave, what comes next after conventional silicon CMOS microelectronics. So with that strategy in mind, we began to make our case. We reached out, built a group of partners and stakeholders. And then, as many of you may remember, about a year ago, the state of Illinois passed its FY25 budget, and that budget included $500 million for this project. So we've been sprinting since then, since last summer. The Illinois Quantum Microelectronics Park is a physical location on right on Lake Michigan within the city of Chicago, 128 acres. The purpose of this facility, or this really will be a campus, a research park, if you like. The purpose of the facility will be to support the scale-up of quantum computing. So that's the singular focus. I mean, you've heard about several different types of quantum technologies already this evening. We're focused on quantum computing, and we're focused on enabling the scale-up. So quantum computing is something that already exists. You can go out and buy a quantum computer for yourself if you have $75 million to spend. These current machines are in some ways prototypes and are demonstrating the kind of computing that we hope to do at a much larger scale within a few years. But to scale it up, it takes infrastructure. I think this was mentioned in some of the previous comments. It takes infrastructure. In some cases, it takes space. In some cases, it takes really specialized industrial scale infrastructure. So we're putting that together at the Illinois Quantum and Microelectronics Park for hardware scale up. There's also a piece of it that's going to be focused on software and algorithms. So we have we've launched a National Quantum Algorithm Center that will also be located at the park. Since we set this up, we've had several major industry partners join us, and we've got others who will be coming on board soon. There are a lot of dimensions to talk about. I also want to just mention how excited we are about the impact that this could have in our state and in our city, in the city of Chicago, and especially on the south side. You may know that this project is going to be located at the former U.S. Steel Southworks site in a part of the city that has had a historical disinvestment for quite some time. We're excited about what this could do for the community and for the residents, for the neighbors. And so we're very committed to making this work on their behalf as well. But the science is just super exciting, and that's I think a lot of us, my partners here at Argonne, partners at Fermilab at University of Chicago, all of my many colleagues at the University of Illinois Urbana-Champaign who are working in this area, we are so excited about this, and I hope you got a sense of that already. So there's a lot more to talk about. There could be a lot of exciting announcements soon. We are expecting to break ground very soon, so stay tuned. And I think I'll stop there. I don't have any other slides or anything to share, but I'll be joining the rest of, I think, the speakers in a panel discussion now. So thank you. All right. So should I stay up here? Okay. All right.
Thank you, Harley. And I invite all the presenters up now to take a seat for a panel that's going to be moderated by Michael Norman.
All right.
So how we're going to do this is I'll ask a few questions to the panelist, and then after I do that, we'll open it up to the audience. Okay, so I'm going to start with you, Jifei. And so you talk about qubits. What are you looking for in a qubit? What makes a good qubit?
That's a very good question. So the kind of things like what we're looking for in a qubit, it's 100% tied to the type of application that we want to use it for. For example, for GPS or any magnetic field related sensing, then the qubit need to be like, okay, operating at room temperature under ambient condition, that's the key, and also with high sensitivity, which ties to that qubit being robust and not seeing too much disturbance during a time scale where all the measurement can finish and pinpoint the magnetic field. And for application like communication and networks, what one cares is a lot on what is the actual frequency and how it can interface with fiber-based network, or if you talk about space, then how can it kind of like interface with that infrastructure better in minimize any turbulence from the air causing problems, things along those lines that bring down to the kind of development of materials and what are the kind of figure of merit that one need to reach. Yeah.
Thank you. Thanks. Salman. A Yogi Berra question here. It's difficult to predict when we'll have an actual functioning quantum computer, so maybe you could tell the audience a bit what are the primary challenges to make such a thing happen.
Right, so this could take hours, but so this is something that people have been thinking about for a long time, right? So I went to the first meeting on quantum computing, which was in Washington, D.C. in 1994. So that was like quite a long time ago. And the big problem then was, can we make a qubit at all that sort of is reasonable? And within a few years, people could make a sort of qubit or a few. And things have come a very, very long way since. Nevertheless, the quantum computers we have now are still toys. And your laptop is way more powerful than any quantum computer that currently exists. So that's interesting. But the important point is that progress is actually very rapid. One of the interesting things is that there are many different kinds of qubits, and they are all in a pretty good state technology-wise. But the big question right now is essentially scale up. So I think the issue of can a quantum computer work is a done deal. Quantum computers can work, but can they work efficiently at scale? That's the big question. So can we make millions of qubits and all of them, really, really high quality and all of them able to interact with each other in a way that produces a coherent answer? That's one question. The other big question is controls, because the qubits, some of the qubits are intrinsically very good. Other qubits need to be carefully controlled with electronics. And so it turns out that you will need a lot of classical computing and classical controls to keep the whole thing working. So it's a very important engineering problem. It's not necessarily just a physics experiment, because that age is over. The other big problem is that quantum computers are extremely error prone. And so if you want to get a reasonable answer out of the machine, you have to have very high quality error correction, which is something you don't need for classical machines. So big advantage of having a classical bit, which is 0 or 1, is that it's unambiguous. It's either 0 or it's 1, good. And occasionally you can screw it up, but usually it's actually pretty good. But quantum states are extremely fragile, so they have to be error corrected, and fault tolerance is an extremely important concern. And what happens is that if you use fault tolerance, you may have 1,000 qubits, but out of them you may only create one logical qubit, one useful qubit. So that's another big issue. Finally, there's also a question of timing. This is kind of a strange situation, but it's important to keep in mind that while quantum computers at scale, which is what we would like to have to solve really hard problems, let's say in quantum chemistry or quantum material science, might be with us in, say, of the order of a decade or so, classical computers are also moving very quickly, and things like AI also produce an alternative way of doing things. So there's competition between techniques. And there's also collaboration between techniques. So you might end up having hybrid systems that are partly classical, partly quantum coming together. So it's a very, very interesting area. And I would say 10, 20 years is probably my guess for the big quantum computer, but that's what it is.
Thanks, Salman. So Preeti, I think people maybe naively think being quantum, you have to have a PhD, but I think the estimate is probably 90% of the workforce will not be PhD. So we would talk a little bit more about the ecosystem and workforce.
Sure. Yeah, so, this is true not just for quantum, but as industries mature, you need more than just PhDs to advance the science and industry. So, sure, in 1994 or even 2000, when someone was talking about the beginnings of when we started looking into the science, you really needed to have a PhD in a relevant area to be able to work in this field. We've come a long way since then. We can talk about it as an industry, and we know it's going to grow. So now it's not just PhDs. We do still need the PhDs, but we also have lots of engineers. We have lots of technicians who are working in this effort. So the labs where we're building quantum computers or quantum sensors, operating these networks, require a lot of complicated equipment, and we need technicians to build the equipment, to run and operate and maintain the equipment. We also, as we are growing companies, like we have companies with several $1 billion of valuation and hundreds of people. Those employees include not just scientists and engineers, but we have, very importantly, people with communication skills who can talk about what the company is doing and talk to the external public, talk to Wall Street, talk to government. So you need to have those skills which overlap with quantum to be able to translate what's happening within the labs and within the companies to the external world. You need HR professionals who know what it takes to build a cutting-edge technology and a company building a cutting-edge technology. You need lawyers. You need people who understand how do you write patents in this field. Again, this is a sign of the field growing, that you need all of this. And, we also have people who are building theater and games that teach quantum to the public. So there's arts and communication involved. So really, there's no limit to it, right? Like, think about what you're doing and think about how that can intersect with quantum. And there's a lot of exciting work to be done because we're still building the field.
Thank you. So Harley, IQ&P is sort of interesting. You're bringing government, sort of the labs, but also organizations like DARPA. You're bringing universities, and you're bringing companies. So it's quite an interesting mix. And what do you think about the advantages of bringing all of these entities together at the same place, and what it will lead to?
Yeah, that's right. So I think the key word is public-private partnership. And it's hard to think of an example of a public-private partnership on the scale that this project represents. You have the universities providing not only some of the basic science, but certainly the workforce that will be needed. You have the state and federal government both putting in resources that attract businesses and will help to grow the industry by providing incentives, right? And that's a huge part of it. But the quantum industry itself right now, the quantum computing industry itself right now is very interesting because it's not just startups, although there are a lot of startups, but it's the giants. It's IBM, Google, Amazon, and Microsoft. So you see all across the industry this spectrum. That each have their own technologies. So all of the three pieces to this partnership play an important role. What we're seeing with the companies that are interested in participating in this project is that they're attracted by, of course, the incentives and the infrastructure, But they say that what really sets us apart is the base, right? The talent coming out of the universities and the existing workforce and the national labs proximity. So there's a synergy. I mean, it's not simple to put all this together. It's quite complicated, but it's rewarding to see us making progress in this novel way.
Thank you very much, Harley. So how we're going to arrange this now is that people have questions, they can line up at the microphone, and we'll go through questions, and then people who are online, they can put their questions in chat, and we'll get to as many people as we have time for. So we now open it up to the audience here. And I think
we have our first question from...
We will be passing the mic so you can come and queue up here.
All right, first question is, can you recommend a quantum computing for dummies level text or resource to learn the basics?
There's a book you can buy on Amazon, Quantum for Dummies.
There is
right?
one.
There is.
It's actually called Quantum for Dummies.
There's even Quantum for Babies.
Right. Yeah.
Chris Ferry is the author. But there are several books depending on the level at which you want to approach it from.
So there are picture books
I would
as well.
recommend a book called Quantum Computing from Alice to Bob. I think something like that. It's a really nice book. It requires a little bit of math, but I think it does a really good job. Yeah. So try to find that one. Yeah.
Go browse at your latest Barnes & Noble, right? So you can probably find something there.
Or send me an email. I'll give you a list.
Or we can give you rec.
Thanks for taking my question. Pretty, this kind of leads to what you were talking about. I've always felt that science and technology help lead society. And when I saw the PsiQuantum facility in the south side of Chicago, I was so excited. I was born and raised in that area, grew up in that area, attended Chicago State University, which is very close to that location. And I'm wondering, are you guys partnering with the local universities and high schools in that area to pull some local talent? We talked about all the PhDs that are needed, but you have a university that's really good right there and lots of young talent that could be pulled into working at that facility. I wondered if you had any plans for things like that.
Yeah, absolutely. And Harley and I can both answer this together. So CSU is doing some really amazing work, and the president of CSU is in fact on the board of the IQMP. So from day one, we're working very closely with them, but we're also working very closely with schools in the area. In fact, PsiQuantum, you just mentioned, they've funded a program at Bowen High School. Yeah, and we've had several community meetings at Bowen High School, and we're working with them to develop programs. That is absolutely the intention, and we're just, any ideas you have, anyone who wants to be engaged, we would really welcome that.
Yeah, I would just add, City Colleges is part of the board of IQMP as well, and we have some growing programs with them.
Hello. Can you hear me?
Yep.
Okay. Well, disclaimer, I'm not a scientist in the classical sense of training. I'm an Illini. I went to Penn. In fact, my last lecture or last final was actually in the place where I believe ENIAC kind of came about and computers and things like that. So my question concerns last week was the 81st anniversary of D-Day. And I had an opportunity to talk with a pretty credible scientist or meteorologist, a weatherman. And this individual, reminds me of the use case that basically enabled ENIAC, which was, basically was predicting the weather. Mm-hmm. And I'm just kind of reminded that, well, first of all, Eisenhower wanted to have it on June 5th. Because there was weather issues, and I know the Germans didn't think everything was going to happen until the 10th. But anyway, it happened on June 6th because there were 3 teams, or 2 British and 1 American team that was advising, I guess, the meteorologists that advised Eisenhower. But anyways, it went June 6th, and I believe that, I got this little device in my hand that allows me to do a lot of cool things. My iPhone was enabled because of things like ENIAC, which I'm going to simplify, forgive me. Again, I'm just a sci-fi enthusiast who believes I already envision a day where quantum's every day, climate change is solved, cancer is a relic of the past. And so my question really relates to that moment where, Einstein's, again, I'm oversimplifying, but Einstein's theories were pretty much proven by, ENIAC's ability to predict the weather or enable things like, D-Day and ultimately, what happened, ending in World War II. And I feel like right now with all these different competing, topological qubits or superconducting, circuits and things, psi-quantum with photonic qubits and trapped ions and all kinds of great, cool technologies. It just feels like it's kind of like a similar moment, and I'm wondering, what is that moment? Again, forgive me, I'm not the scientist. I don't know. I'm oversimplifying. Forgive me, but I just feel like there's some use case or some moment that could just bring everybody together, because I feel like there were these competing schools of thought 80 some years ago, which why would you want a freaking electronic computer? Like that doesn't make any sense. You want and basically ENIAC proved it. And I feel like right now, something like that is needed. And I'm just wondering, is there that you could share with me as a civilian that could maybe accelerate things, which is ultimately going to happen?
This is actually a very, very important question. So, and fundamentally, the answer, you will not find this satisfactory, is that we don't know. And at the moment, this is actually one thing that was mentioned earlier, was that there needs to be some pretty massive progress in quantum algorithms. So one thing that's pretty clear is that when you have a quantum computer, it changes the landscape of computing. So this is what the question referred to, basically, because historically, the first digital machines changed the landscape of computing. So what quantum does, it says that certain problems we thought to be hard might be easy. Certain problems we thought were hard will remain hard. So that's just a fact. So once the machines get sufficiently powerful and we get smarter, which is a lot slower, then we might be in a better stage to answer this question. But this is the question that keeps us all awake. What is the killer app? And we're waiting for that. We don't have it yet.
But
So
I want to say one thing, and that is it's already affecting your lives. So the federal government has decided to change encryption standards that you use when you do online credit card transactions, because a quantum computer can hack it. And they think that a functioning one could come about within the next decade. And so to get ready for this, they're already starting that process.
Yeah.
I think Salman mentioned this before. I think because of advances in quantum computing, we're also figuring out other ways of doing classical computing better, faster, more efficiently. So that's a side effect. And then just going back to the ENIAC example, I think at the time, we didn't know all of the things that we'd be doing with the computer. Nobody had imagined an iPhone that I'd be spending hours on TikTok. I don't have it on my phone.
That's not a good application.
Yeah. But it was more for calculating projectile trajectories. So I think, I forget who this should be ascribed to, but the idea of technologies like this, it's like we're almost certainly overestimating the gains in the short term and completely underestimating what it can do in the long term. Right. We just don't know what the applications will be when it's here.
Okay, I think we have your two best questions of the night.
I was hoping for a more thorough explanation on the inability to clone quantum information.
So Mike, you want to do this? You want to do this?
You want to take that one on?
That's.
So basically, I can try to answer this. So what this basically refers to is the idea that classically you can copy something, right? So if you say, well, I have some information and I want to do some calculations with that piece of information, I can just make multiple copies and I can do different calculations on each copy, for example. So if, let's say my calculation scale is limited, so I do some approximate calculations on one piece of this, another, and another, then I can put them all together and try to improve my result. quantum mechanically, this copying is forbidden. There's a theorem called the no-cloning theorem, which basically says you can't take quantum information and simply copy it. This is what was referred to earlier by Mike when he was saying, if you copy it, you destroy the original. So you can have a copy, but it doesn't help you because you don't have two of them, so you can't work independently on those two. So you cannot get what people call parallelism naively because you only have one copy to work with at a time. So in classical computing, there's something called fan-out, which is a possibility of using multiple states, and quantum computers cannot use this capability. So that's one reason why quantum computing isn't as simple as it looks.
Yeah. So one thing you think about, you have the surface of the sphere I was talking about, like the surface of the Earth. Because this quantum bit can enlist on the surface, and it has a latitude and longitude, that is connected with why you cannot copy it. So first approximation.
That's a good question.
You know how like I heard that like for every like one logic gate qubit you have to have like a lot of other qubits to check it. Is there like a simpler way we can like check it without having to like absolutely fill up the computer with like checking qubits? No, yeah.
That's $1 million question.
Yeah.
The companies are working on.
So in principle, so the answer is if you had a really, really, really high quality qubit, then you wouldn't have to check it. So one way to improve the situation is to produce a qubit that is so high quality that nothing ever goes wrong with it. But this idea of embedding a qubit in a whole bunch of other qubits is also very interesting. And the whole question is, what is the smallest number of qubits that we can do this embedding in? So if it turns out we only need a handful, like 10 qubits, to basically stabilize one qubit, that's not too bad, right? Because if you take, for example, a chip can have trillions of transistors. So if it turns out that we can have trillions of qubits at some point, and so what if 10 of them are used to stabilize one? We still have plenty left over, right? So it's also a question of how the technology scales. So if you can scale it sufficiently, then you don't worry about how many qubits are needed to fix one of them.
Yeah, and that is kind of the overhead the field is trying to work on to overcome and to reduce that number so that you get better scalability. It's all because quantum states are so fragile. You write it in a particular state, and with noise, it changes. So you have to have multiple other qubits around to check it and do the correction. So that's, yeah.
And this checking is very subtle. It's not the same as in classical computing, where also you do similar things. But in the quantum case, it's much more complicated.
Hi. So my question is a little bit connected to ENIAC and older computers. So when it comes to current practical quantum computers, how different are they from just miniaturized analog computers?
They're actually much larger. Yeah.
No, sorry, just say that again. How different are they from?
Are you saying, would you ever have something like this in your pocket that was a quantum computer?
What I'm saying is the qubits are continuously variable, right? They change like an analog variable. So, we had analog computers in the past that kind of performed the same functions. So I'm trying to understand how those two things are different.
I still don't get the question. I mean, so you mean in terms of miniaturizing what you have, or?
So I think when you do quantum computing, you can do digital or you can do analog. But quantum is very different from classical. So how, even in the analog mode, how the machine functions is very different than how a classical computer functions in analog mode.
Yeah. I mean, I would say one other thing is, which is classically you can make, because the classical computing is so robust, right? You only switch. So you can make switches that are very, very small because they don't interfere with each other. Quantum mechanically, you have this problem that you don't want the qubits to have bad interactions with each other, which are uncontrolled. So even if the qubit itself is small, you don't want a lot of qubits to get crowded in some chaotic ways. So it's not so easy to miniaturize a quantum computer necessarily. So as compared to a classical system.
All right, we have an online question.
All right, we're going to collapse a couple of these online questions. There are several on the ecosystem of partners, businesses, opportunities for small companies. So let's hold that. But a really great question about that starts with prairie ecosystems are rich in biodiversity and are among the rarest and most endangered biomes in the world. Could industrial partners in the quantum prairie possibly be engaged to contribute to prairie restoration in the region?
So I can that's a good question. I try to answer that. So I think one of the things that we're very excited about in the large IQMP project is that the technology is pretty environmentally friendly, and it's going to have a pretty light footprint, and it's certainly true that there are fragile ecosystems that we need to be thinking about. You know, long term, the value of having quantum computing at our disposal is something that could transform our ability to live sustainably. You know, I think that's one of the use cases. That could be a killer app, right? That we could end up with in some years. Ways of living more sustainably, alternative energy, ways of reducing emissions. So I think it's a good question. It's complicated, but I think we think of these kinds of technologies as someday enabling a more sustainable, a more sustainable lifestyle. So that's what I would say.
All right, we've wrapped up the Q&A. For the folks who are in line, the speakers will stay after, so you're welcome to go up and speak with them. I'll invite Megan back to the stage to wrap up.
Wow, what great questions. I'm not sure how old two of those questioners were, but you stumped a bunch of scientists, which I love. So thank you, everyone, for really engaging in that Q&A, and thank you to the presenters again for your talks. Fascinating discussion. We really hope you all enjoyed our latest installment of the Argonne Out Loud public lecture series. It's been a pleasure to spotlight really the growth of quantum science and technology and the role of Argonne and our partners are playing in shaping the future. Before we say goodnight, I'd like to draw your attention to the slide behind me. The QR code you see will take you to a very brief survey where you can answer just a few questions about your experience tonight. So if you are so inclined, please take a brief moment to complete the survey. We really value the feedback and use it to make future Out Loud events even better. So thank you again all for joining us, and have a good evening.